welcome. Today we're going to talk about electric potential energy and something called electric potential, which won't get confusing at all. All right, if you've ever done gravitational potential energy, it might have been a year ago, but if you've got two things really far apart, or no, we did this recently. All right, so for gravitational potential energy, your formula is negative some constant, universal gravity constant, times the mass charge of the first thing times the mass charge of the second thing divided by the distance between them. It's always negative because things have zero potential energy when they're infinitely far apart, and it's negative if they're any closer than that. So this can only ever be negative. So we got constant, charge 1, charge 2 divided by distance between their centers. Electric potential energy is pretty much exactly the same idea, but with electric charge now and a different constant. That's it. So if you want to find the electric potential energy, now usually we abbreviate this with capital EP instead of just a capital E, as we did for electric field strength. So this will get confusing. EP, potential energy, just E, electric field strength, which are two very different things. This is a scalar, electric field strength is a vector. So try to keep those straight. EP, potential energy. It's measured in joules. You've got the same K we had before, 9 times 10 to the 9, coulomb is constant. And then we got the charge in coulombs of the first object times the charge in coulombs of the second object divided by the distance between their center squareds. And that'll tell you the potential energy of any two electrically charged objects some distance apart. Now, with electric field strength and electric force, we kind of just found, we usually didn't use the negative or positive, we used that to figure out what direction they were pushing or pulling, and then we just use that direction with the magnitude of our result. So we used kind of negatives and positives in the beginning to figure out the direction, but then not so much in the formula, unless we wanted to just figure out if it was attracting or repelling. With electric potential and electric field strength, we will always use the negatives. As these are scalar quantities, we don't have to figure out direction. The reason we didn't before is because we'd have to use them to the negatives, positives to figure out the direction. And then we don't want to kind of double count it because we've already used that information. In this case, the only way to use the information is by putting it in the formula. It's just straight positive potential energy or negative potential energy. So if you have two positively charged objects or two negatively charged objects, this whole thing will end up positive. Positive times positive is positive, or negative times negative is positive. So this whole electric potential energy will be positive if they have the same charge. Keep in mind that just like gravitational potential energy, you've got zero potential energy when they're infinitely far apart. And you have more potential energy than that if you bring two like-charged objects together. It's kind of like they start off infinitely far apart, and you got to kind of compress the spring. That's kind of how I think of it. You got to squish them together. You got to do work to bring them together. And if you release them, you can harness that to do other work. Whereas if they're negative and positive, if they have opposite charge, they will try to come together as quickly as they can. They will attract, and so it would take more energy if they were together to separate them infinitely far apart. So negative potential energy if they're opposite charges and attracting, just like gravity attracts and it's negative potential energy. If they're repelling, it's positive potential energy. One interesting thing with this, before we had to potentially make a triangle if we had, say, one electric force or electric field strength west and one electric field strength or force north, we'd make a little triangle and figure out what the magnitude and direction of the net force or net electric field strength was. You don't have to bother with any of that with potential energy because it's not a vector, it's just a scalar. So if we had this arrangement of particles and we just wanted to figure out the total potential energy of this guy because of these other two, we just have to figure out what the potential energy is due to these two and the potential energy due to these two, and add them up. Just straight adding, no triangles, no anything like that. And it does not matter the arrangement. Like, you could change this arrangement as long as the distances stay constant. It could be in a line, it could be anything else, and your potential energy will be just the same. So you just basically plug it in. In this case, I got like plus 1 coulomb, plus 1 coulomb, minus 1 coulomb. So in this case, it would be K plus 1 coulomb times plus 1 coulomb divided by plus 1 coulomb plus K times plus 1 coulomb times minus 1 coulomb over 1 meter. These will cancel in this particular case because they'd be equal and opposite, and so the potential energy of this guy due to the other two is 0 and does not depend on the arrangement. It can be as wacky as you want, and it's still just as easy to solve. Just straight put the negatives in the formula and add them up. That's all. Yeah, and electric potential is basically the same idea. It's measured in volts. A volt is a joule per coulomb, which maybe you remember from electric circuits last year. So volts are joules per coulomb. Joule is the measure of potential energy. Coulomb is the measure of charge. So volts, your electric potential is equal to your potential energy divided by your charge. This is a formula. It's also kind of a definition. Just think of the units and it makes complete sense. You can rearrange it to be whatever. Yeah. Sometimes this is change in energy. This could be change in electric potential, and this could be change in potential energy. Yeah. Anyway, and we can come up with another formula for a point charge. A lot of what we've been doing so far has dealt with point charges. We'll get to plates later. Anyway, so we can come up with another formula since our electric potential, our joules per coulomb, kind of a measure of energy per coulomb, is we could just put our formula for potential energy divided by how many coulombs is kind of causing the voltage, and we end up with this formula. So, or the one that's in the field, not the one causing it. So this guy right here is another one of your formulas. Here are your two main ones. So you got your electric potential equals your potential energy divided by the charge causing it, or sorry, charge in the field. And then this guy right here is what happens when you take your formula for potential energy and then divide by the charge in the field. You're left with the charge causing the field, and so your electric potential, your voltage, is equal to just KQ over R. Yeah, and again, it's a scalar, so we could have some crazy arrangement and it will end up working the same. You can just, if you want to find the electric potential at a point, you can just do KQ over R plus KQ over R for however many charges you've got creating a voltage at a point. This is very useful for finding the, like if you can find the change in electric potential, the change in voltage, you can find the change in potential energy of a particle moving between 2 points. And almost always that change in potential energy becomes kinetic energy. And so there's a lot of before equals after here. So tons of before equals after, where you can use either your full potential energy formula, which we talked about before, or you can use your electric potential. By the way, electric potential energy and electric potential are super confusing. Do be careful. Electric potential energy is just total joules based on 2 points. Electric potential is basically, you've got kind of a field there, and so it's kind of the potential energy per coulomb of charge you put at a point. There's usually a point much like we did with electric field strength. Hopefully this helps. I don't want to go on too long. Thanks for listening, and have a great day.